So about us, actually, this is a kind of a interesting project. I'm Cesar. I work for Apple, and my two presenters are Lei from Bloomberg and Huaxiang from Cloudera. And this is kind of an interesting story. So Bloomberg and Apple Siri have been working on Read-Replicas for a while without kind of knowing that we were fighting the same fights. And through some talking on mailing lists, we found out, hey, you guys are trying to get this up and running, so are we, and there was some back and forth for a while. And then we went back to our separate caves and kept working on it in our deep, dark basements. Last year at HBaseCon, we kind of tripped over each other and started talking. It's like, hey, how's it going? And they're like, oh, we're having these problems. Like, oh, we solved them this way. We were having these other problems, and Bloomberg told us, oh, we solved them this way. And then we had questions, and we didn't know what was going on. So we're like, oh, I know a guy. So we went and grabbed Dennis. And then we went around, and then we grabbed Esteban. And then it turned out to be like 5 to 7 people standing around outside while there were some other talks going on. And it's like, so let's work on this together. So this is kind of the story of a year's worth of work where we went across companies and across the open source to get this up and running. So it's pretty exciting. So just some opening remarks on how it is. We're just going to talk about, the different environments, being that it's multiple companies, different approaches to the same problem. Battle scars, as per usual. And at the end, we're just going to kind of talk about how it went. So one thing that's kind of was a big initiative for a while was this MTTR, the Mean Time to Recovery initiative. And this was ways of modifying HBase. So when there's a catastrophic failure, it can come back faster. Or if there's events that happen, it can recover a lot faster. Some of the sub-projects of this MTTR was the assignment manager, which, great, it's made it into HBase 2.0. Very happy, can't wait to play with that. Another one was this Read-Replica concept. And the Read-Replica concept is this idea where HBase is great, and HBase will keep your data safe. That's the promise that HBase makes. The problem with keeping your data safe is that when it goes away, HBase kind of decides, okay, your data's not safe. Therefore, it doesn't give it to you. Lars kind of talked about the CAP theorem this morning. I'll let the smarter people talk about the CAP theorem. But what really the Read-Replica system does is kind of switch the weights of the CAP theorem. So when you write something into HBase, and this morning there was a great overview on the right path on how HBase work. So if you guys got to watch that, great. What happens is you write your data into HBase, and then that data is written to a secondary replica on another region server, and that is read only. The way this kind of works is if you can't get at your real data, you'll be able to get something out of another region server that's somewhere else. So if you can do it fast enough, you shouldn't notice any difference between your primary region and the read replica. If it's slowed down, the data on your read replica could be stale or old. On the client side, you have to say basically, I want to do a timeline read, which means I am going to take my life in my own hands, and the data that comes back may or may not be the same data, but at least I'll get something back. We'll talk about through the presentation on why that's important. But as you can imagine, for applications that need to be up and have data, that is pretty critical. Just to be clear, this is only on the read path. There is no good solution for the write path. HBase, when you write data into HBase, it's either safe or it'll tell you, nah. And then you have to decide what you're going to do about it. So hopefully that's clear as mud. So over at Siri, this is a little bit of how we work. Siri from day one has used HBase as a backend. Anytime you do a Hey Siri joke and ask her to do something funny, that query goes over to HBase. So every time you get home and you say, Hey Siri, turn on the lights, you are turning the lights through HBase, which is fantastic for this conference. We have multiple data centers all over the world. They're distributed. What we need for Siri is all of this to be as fast as possible. That's where we keep models. That's where we keep everything. So we do very basic stuff, gets and puts. That's all we do. So as you can imagine, for us, it's very critical that those gets and that the gets come back very quickly. The puts we can sort of wait on. We can deal with some exceptions, but we need the data to come back. And stale data is better than no data whatsoever. So that's what we care about over on the Siri HBase. Now I'll pass it over to Lei.
Okay, thank you guys. So, okay, go back. Okay. HBase at Bloomberg. I think Biju gave a very good presentation and about the numbers we have. So HBase is widely used and shows very good performance and scalability. And for this talk, the read replicas are most beneficial to applications that has these three features. So if it's read heavy, and also it's very sensitive to latency, and also it has some tolerance to stale data, or the data is only write once and read multiple times, that's a very good applications to use read replicas. And this is the things we have done at Bloomberg to test read replicas. First, we have it tested in lab cluster and got like some of the issues, and that's when we started to cooperate with like Cesar and Huaxiang to figure out what's the solution. And after that's all patched, then we tested it again in dev and beta, and everything went fine. And then we can like pressure test it on a dev cluster where like we have a very heavy used cluster. And at that time, we saw some of the region servers died out of memory. So that's when we like stopped pushing to production. And the plan we have is now we want to have more in-depth monitoring on the memory and network, and then have more tests. And after that, if we have everything tuned, and then we plan to have a long running test with production data to prove it's like stable enough for in our like environment. So so the most a typical case in our case is like to help in case of region server failure. So let's say in this, if I have a test environment, it's like a dev cluster with 10 worker nodes, and the clients are making 100% read. And the table I'm using for this test is like from PE, and it's a typical table, and I have it's like 100 pre-split. So that means around like 10 region servers per 10 regions per region server. And here is the graph. So the clients are making 10. Oh, I have 10 threads. So each of them is making about 10 requests per second. And each of the requests will report its latency at the beginning of the request. So, and also each thread will wait until it gets like the response. So which means the timeout is longer than the recovery time. So from the graph, we can see on the y-axis, the unit is second. So most of the requests, the average of the latency is around 2 milliseconds, which is like along the x-axis. So I have one region, like one worker node powered off at around 41 seconds. So immediately, since the clients are making random reads on like any of the row, so that means it has 1/10 of the possibility hitting the failed region server. And once it's got the failed region server, the latency is very high. So the first couple of requests is like about 50 seconds. So that's when it powered off, and eventually, like about 15 seconds, all the 10 threads all got to the powered off region server and got stuck. So the recovery time for this region server, it took around like 45 seconds. That's by the default setting. So for Zookeeper, the tick time is around 2 seconds, and the default timeout for the session is like 20 times of the tick time. So the failure detection is about 40 seconds, plus some the reassignment of the regions and all the replay of the writes. The total time is around 45. So that time is tunable, but in most cases it's more than 10 seconds. So for some of the applications, 10 seconds recovery time is way too long. So that's when we have the region replicas help. So in this graph, so the most important thing is like on the y-axis, it's millisecond. It's not second. Okay. So here, how the replica works is like the clients will make a primary request to the primary region. If it gets the results within that primary timeout, then that's fine. But if it does not receive any results after that timeout, it will make another request to the secondaries. So in this case, I have set the primary timeout to be 10 milliseconds. So you can see on the graph, all the oranges are the results from the primary, and the blue ones are results from the secondary. And similarly, I have unplugged a worker node around like 43 seconds, right? Yeah, 43 seconds. And the only thing I observed is like there are slightly more secondary reads. But the good part is there's no downtime at all. So that's a very helpful thing we have in our clusters. So what's the cost of read replicas? So it comes with a cost. So first is like since as Cesar has introduced, there are two ways of the writes, how the writes gets propagated to the secondary. The first way is to for the secondaries to refresh periodically about the H files, and the second way is for the primary to send the word replication to the secondaries. So in case of the asynchronized word replication, then the secondary region servers will use as much memory as the primary. So that means overall the memory consumption can be doubled. And also we will have higher network usage since the word will be replicated over the network. And also if it's the primary call timeout, if it's not tuned properly, the clients potentially can make a lot of duplicated requests to both primary and secondary. That means that can cost some overhead. So in order to show that the memory and also the write propagation, I will do a write test. And in this write test, I will write a table size of 10 GB. And on the client side, the write rate will be 10 megabytes per second. And in order to be simple and show nicely in the graph, I will not enable region splitting. So there will be only one primary region and one secondary region. So this is from the region server, the primary region server, who is receiving the data from the client. So you can see it confirms the total input rate is about 11 or 12 megabytes per second. That's maybe 1 or 2 megabytes per second overhead. And this is the memory size, the mem store size from the primary. So this is without the replicas. Only the primary reports the mem store for this table. And now look at the left side. That's when the read replica is enabled, but the asynchronized word is not enabled. So the orange lines are the primary mem store size, but the blue line at the 0 would be the secondary. That means the secondary region server is not using memory at all for this table. So that's the same case as not having replica regarding the memory consumption. But on the right side, if the asynchronized word replication is enabled, that means the primary will ship the words to the secondary, and the secondary will make the change in save the change in the memory. So that's keep in mind that can double the memory consumption. And this is the network. Actually, the increase of network usage is not as bad as we thought before. So on the left side, it's the outgoing traffic from the primary. So when the clients writes to the primary first it needs to send data to data nodes, and data nodes need to replicate to other data nodes. And also, that's only the left side case. So the primary region server will not ship the word to the other side. So that's on average, that's about 64 megabytes. But actually, there's a big chunk at the end. So I think that's maybe something else. But on average, that's like 60 megabytes per second in case of like 10 megabytes from the client side. On the right side, I have the asynchronized word replication enabled. That will add only like 10 megabytes per second. That's primarily the word replication. So that means even it's enabled, so the memory, the network increase is about like 15%. So that's what we observed from the test. Okay, here's the primary call timeout. So this graph shows on the client side how much the traffic is from primary and how much traffic is from secondary. So on the left half of the graph, the primary timeout is set to 10 milliseconds. So that's what we had before. So in that case, like almost all the traffic comes from the primary, and the secondary does not, it's not used at all in this case. But when I set the primary timeout from 10 to 1 at the middle, then immediately the secondaries are getting request. So in this case, the average latency is around 2 milliseconds. That means like maybe half of the request will time out, and the client will make request to the secondary. And in the test, we observed about 60% of the load on the secondary compared to the primary. So that could be a significant load on the client side network, and as well as the server side. So the suggestion we have is the primary latency could be set to 5 times of the average latency. But that depends how much you want the request going to the secondary replicas. If you don't want it at all, maybe you set to maybe 10 times. Yeah. So that's the suggestion. So now I will pass to Huaxiang for some of the insights.
Hey, so my name is Huaxiang, and I'm HBase engineer from Cradella. At last year's HBaseCon, some of us met and we decided to make Read-Replica production ready. So today I'm going to share, we created actually HBase 1823 upstream to track the effort. Today I'm going to share with you a few issues we found and fixed along the way. So the first test we did is to kill a region server process. We found lots of get errors in this test, and the Read-Replica is not working. After some debugging, we found the root cause. So as you can see from this diagram, HBase client sends a get request, a get RPC to the primary replica region. So since the primary region server is down, so the client will get a connection reset exception in this case. So the client is supposed to catch this exception and send the get RPC or get request to the secondary replica region. But in the old client logic, it did not do that. Instead, the HBase client just directly throws the exception out to the application. So we fixed this issue, and we also fixed a few other issues found during code review. So with these fixes, we rerun the test, and there's no get errors. So far so good. So the second test we did is to power off a node hosting both region server and data node processes. Again, we found lots of get timeout exceptions in the test. We enabled the HDFS hedged read, and this helped a lot. But still, there are lots of get timeout exceptions. This issue actually took us quite some time to figure out. So I'm going to share with you the details we found. As you can see from this diagram, the HBase client sends a GET request to the primary replica region. Since the primary replica region primary region server is powered off, so there will be no response. The client wait for some time, and then it will again to send the GET request to the secondary replica region. For the region server to serve the GET request, it needs to load H files from HDFS. So the region server tries to fetch one data block from HDFS. Name node in this case returns a pipeline with the part of data node to be the first entry in the pipeline. So in this example, you will see the pipeline is like DN1, DN2, DN3, with DN1 being part of. So the region server tries to fetch the data block from DN1, and it cannot even establish a TCP connection since the DN1 is part of. So the region server waits until it gets a socket connection timeout exception. And then it will try to fetch the data block from DN2, and it succeeds. The timeout for the socket connection in our case is 3 seconds. So you may think 3 seconds is nothing, but there are many data blocks in one H file, and there could be more than one H file for the region. So the total time the region server spends to serve the GET request is actually n times 3 seconds, with n to be the number of times the previous process repeats. And the client cannot wait for the response forever. After some time, it will time out and report a timeout exception to the application. Yeah, so we worked with our HDFS engineers for a solution, and they found us HDFS 3703. This feature enables a name node to detect a stale data node faster. So after the name node detects a stale data node, it will put the stale data node to be the last entry in the pipeline. So in our previous example, the near pipeline will be DN2, DN3, DN1. As a DN1 to be the last entry in the pipeline. So this is the configures we used in our testing. As you can see, that the interval to detect stale data node is set as 7 seconds. With this feature enabled, we rerun the previous test, and the GET timeouts are greatly reduced, so not totally. So we are still working with our HDFS engineers for a better solution, but at this moment, we thought it's good enough for now. So with data path fixed, there's still one major issue. The issue is that during previous tests, HBase cluster always ran into region inconsistency. And even worse, these region inconsistencies cannot be fixed by HBaseCon. Luckily, we found upstream JIRA, which is HBase 18625. This JIRA has a set of the steps to reproduce the region inconsistencies with Read-Replica. We debugged this issue and we found the root cause. The root cause is that the in-memory state for a split parent secondary region is not set correctly. We fixed this issue and we rerun the previous tests with this fix. So there's no more region inconsistencies. So we thought this fix addressed the root cause. So along the way, we also had to put like fixes like HBase 18024 and HBase 18025 to prevent region inconsistencies from happening. So along the way, we also put in fixes in HBaseCon. So HBaseCon now is able to detect and fix region inconsistencies related with Read-Replica. So all these fixes are checked by HBase 18223 upstream and are available in HBase 1.4 plus and HBase 2.0 plus releases. That's all from me. Thank you.
Thanks, Huaxiang. So Huaxiang helped us test, and then that's kind of the experience we had. This is the testing framework that we had when we were running this. The 1,500 instances is the clients that are hitting HBase. That's not the size of our HBase cluster. And then how many requests per second they're doing it. When we started doing this test, we started shutting down region servers gracefully, see what happened. Then we would like kill 9 the region server, but we found out that no matter what, the best test was just to pull the plug out from the back of a region server. That's how we came about finding all these issues with the data node. If you test just your region servers, I think you're missing about half the equation. So when you're testing any sort of DR type situation or worst case scenario, don't forget we're highly coupled to HDFS still. Maybe in HBase 3 we will be less. I'm gonna have to have a longer conversation with Lars because I believe data locality really matters. I want to take his perspective on why he believes that's not the case. Our testing shows it. If you guys haven't played with the hedge reads for the data node client libraries, definitely worth spending some time on it. When we were testing, actually, there was a point where we thought that even if we didn't get read replicas to work, just the improvements with the hedge reads were going to be enough to make the whole project worthwhile. And then we're running 1.x version of HBase with a whole bunch of forward patches, back patches, and everything. If you're going to play with read replicas, just go to HBase 2.0. Don't try to patch it yourself. So it's kind of interesting that we have the same tool but different perspectives. The testing that we did over at Siri is we want to minimize the number of client-side errors that we see that affect the Siri application. So literally, we had one graph with a single line, and we were trying to improve that. Our first one, when we pulled a line out of the back of a server, this is what the client sees. We're cruising. There is no errors whatsoever. We pull the server, the plug out the back, and we get 500,000 errors just spike up. So that green line is number of errors coming out of the back of the server. By doing all the changes that Huaxiang said and doing everything else, and by a magic trick of a button, now look at the y-axis. It's 1K. So on the client side, that's amazing. Sadly, I could have cheated and got another one. There was one time where we got 6. Not 6,000, we got 6 errors. So going from 500,000 to even 1,000 is a massive change for our customers. So all this work that we've put in is just a massive, massive improvement to the customer base for Siri. I really want to thank the entire HBase community for a couple of things. Even in the Bloomberg talk that came before us, it was mentioned that, you know, when there's a new ticket that comes up, somebody jumps on it and at least has a comment, a question, or an idea on how maybe this is not an issue and you can solve it a different way. And if it is an issue, they'll go for it. I really want to thank the community for helping us with this Read Replica. It's been an amazing experience, and it's been tons of fun. Thank you very, very much. And then it wouldn't be an HBaseCon presentation without settings. So here are the settings that we are using over at Siri, and then the Bloomberg guys are using mostly the defaults. And again, this is just a great example of how you can see the same technology through different lenses. Over at Siri, we're trying to help decrease the number of errors. At Bloomberg, they want higher availability. So default values seem to work. For us, I guess not. If you want to go, mileage may vary as per usual. As you can see, either way is a great place to start. Thank you very much. Have a good snack. And if you have any questions, just come find us outside at any point.